In this video, we're going to talk about stoichiometry. If you're not familiar with that term, I'll define that more explicitly a little bit later in the video. Before we get to stoichiometry, I want to do an example. And so I want to imagine that we're making sandwiches, and we have a particular recipe for this particular sandwich, where we're going to use 2 slices of bread, 3 pieces of lunch meat, and 1 slice of cheese. And so if I combine those exact ingredients, I'll make 1 sandwich. Right? So then the question I have for you, if we used 4 slices of bread, how many sandwiches did we make? And so to make 1 sandwich, I need 2 slices of bread. So if I used 4 slices of bread, of course, I would have made 2 sandwiches. All right, so far so good. Right, I want to do something a little bit different, right? So we take our same recipe, but I want to write this kind of like a chemical equation, right? So instead of showing these pictures, I'm going to say, all right, if I take 2 slices of bread, I'll use B for bread, plus 3 pieces of lunch meat, plus 1 slice of cheese, that's going to give me 1 sandwich. And so now what we can do with the coefficients in our recipe or in our chemical equation, these are related to one another. And I'll go ahead and put the 1 in for the cheese, although, as you know, when we write chemical equations, if the coefficient is 1, we usually leave it off. But this chemical reaction, or the recipe, tells me how all of the ingredients and all of the final dishes or the final products are related to one another. And so if I want to make 1 sandwich, I need 2 bread. If I want to make 1 sandwich, I'm going to need 3 slices of lunch meat. Or if I want to make 1 sandwich, I need 1 slice of cheese. So we know how all the ingredients are related to sandwiches, but we also know how all the ingredients are related to each other. If I make 1 sandwich, I'm going to need 2 bread. But if I use 2 bread, I'm going to need 3 pieces of lunch meat. Or I could say that 2 bread is equal to 1 cheese. Or I could say that 3 pieces of lunch meat is equal to 1 slice of cheese. So I can take any of the ingredients or final products and write how they're related to each other based on the coefficients in the chemical equation. And so if we used 36 slices of lunch meat and I wanted to know how many sandwiches we made, well, I could say, all right, for 1 sandwich, I need 3 pieces of lunch meat, so 36 divided by 3 is 12, and so I would have made 12 sandwiches. That's pretty easy to do when we have nice whole numbers. When we get to applying this concept to chemical reactions, our numbers aren't always going to be so neat. And so what we might do instead is write a conversion factor on how lunch meat is related to sandwiches. And we have that right here. We'd already written it. 1 sandwich is equal to 3 pieces of lunch meat. And so if I start with 36 pieces of lunch meat, and I use this like a conversion factor, I want my final answer to be how many sandwiches, so I need the lunch meat to cancel. And so then again, 36 divided by 3, I'm going to have 12 sandwiches. So what we've just done here for recipes, it turns out we're going to be able to do with chemical reactions. And so this is what's called stoichiometry. Stoichiometry is the study of the numerical relationships between the chemical quantities in a chemical reaction. And so how do the amounts of the reagents compare to one another? And if I use a certain amount of reagents, how many products am I going to make? And it turns out this is an incredibly important concept to all branches of chemistry. When you do organic chemistry, analytical chemistry, inorganic, physical, biochemistry, we're always going to touch back on this idea of stoichiometry and how do we relate the amounts of the different reagents to one another. And so we don't have slices of lunch meat and slices of bread and slices of cheese, the thing that the chemical reaction relates to one another is the number of atoms, although in practice the number of atoms or the number of molecules is not very useful. What's much more useful is that the coefficients in a balanced chemical equation tell us how the moles of each substance are related to one another. So when we're dealing with quantities in lab, we don't want to count how many molecules we have, right? That's what we have the moles for. And so when I have a chemical reaction, I can tell you how the amounts of all of the reactants and products are related to one another. And so I can say, right, I know there's a 1 to be understood in front of the nitrogen, in front of the N2. I can write how all of these are related to one another. I can say that 1 mole of N2 is equivalent to, or will react exactly with, 3 moles of H2. Or I can say 1 mole of N2 is equal to 2 moles of NH3. Or I can say that 3 moles of H2 is equal to 2 moles of NH3. Now, we don't generally need all of these. It depends on what the specific question is asking. So here's an example of how we might be asked about one of these problems. So they say, according to the above equation, how many moles of ammonia are made if 0.245 moles of hydrogen reacts with excess nitrogen? And you'll see this term quite frequently when we do stoichiometry. If we have an excess reagent, that means we just have more than enough. There's going to be nitrogen left over. And so this problem is saying, I have 0.245 moles of hydrogen. How much ammonia is that going to make? And so I need to know the relationship between hydrogen, H2, and ammonia, NH3. And so when I look at my relationships, or if I hadn't written them down, right, I would just write it. I would say, okay, I want to compare hydrogen to ammonia, so it's my 3 moles of H2 is equal to 2 moles of NH3. That's the one I want to use. And so I'll just do this like a conversion factor. I started with 0.245 moles of hydrogen. I want to know how much ammonia I'm going to make, and so I need the moles of hydrogen to go away. And so way back when we first started doing mass and mole conversions and atoms and mole conversions, I said that oftentimes it's helpful to don't just write moles, but say moles of what? And I said it would become important to do that later on. This is where it becomes important, right? If I just used moles, I wouldn't know if I was talking about moles of H2 or moles of NH3. And so we have to be specific. Moles of H2 will cancel with moles of H2. And so my final answer is going to be moles of NH3. So 0.245 times 2 divided by 3, and I get to 3 significant figures 0.163 moles of ammonia. Okay, here's another similar problem. Now, one issue with the last problem is we don't have any instruments that we can put a sample on, and it will tell us how many moles there are. What we do have are devices that we can put substances on, and it will tell us what the mass is. And so most stoichiometry problems in the real world don't go from moles to moles, but they may often go from mass to moles or from mass to mass, because I can use a balance to easily determine the mass. But then, of course, we know how to convert from mass to moles for a pure substance, and that's just using the molar mass. So in this problem, we're not starting with the moles of HCl, we're starting with the mass of HCl. So if we have 17.3 grams of HCl, we want to know how many moles of water can form. And so this is just going to be like a conversion factor, right? The first thing I need to do is I'm given grams of HCl, and I want to convert that to moles of HCl. And so to do that, I'm going to use the molar mass of HCl. And then ultimately I want to get here. I want to get to moles of water. This is my goal, right? And the way we go from the moles of any one substance to the moles of any other substance in a chemical equation is to use the stoichiometric coefficients. So that brings up another important point. I need to be sure that the chemical reactions I'm using or the chemical equations I'm using are balanced. And so I didn't check this before I do the problem. I need to make sure this is balanced so I know what the stoichiometric coefficients are. So go from moles of HCl to moles of water. I'm going to use the stoichiometric coefficients, the coefficients that go in front of each compound in the reaction. Stoichiometric coefficients is just a fancy way of saying that. So to balance this equation, I think what I need to do is, to balance the oxygens, I put a 2 in front of the water. Then I need a 4 in front of the HCl. And now I have 4 hydrogens, 4 hydrogens, 4 chlorines, 2, 4 chlorines, 1 manganese, 2 oxygens, 2 oxygens. So the way I get from moles of HCl to moles of water is going to be that 4 moles of HCl is equal to 2 moles of water. And so the two conversion factors I need, I'm going to do this in 2 steps. I'm going to use the molar mass of HCl to go from grams of HCl to moles of HCl. And then I'm going to use the stoichiometric coefficients from the balanced chemical reaction to go from moles of HCl to moles of water. So the molar mass of HCl is 35.45 for the chlorine, 1.01 for the hydrogen, so it's 36.46 grams per mole, or I often like to write that as 36.46 grams of HCl is equal to 1 mole of HCl. So the two conversion factors I'm going to use are the molar mass and the stoichiometric coefficients. So I'll take my .3 grams of HCl. I'm going to use the molar mass first. And so the grams need to go away. So I'm going to put the 1 mole on top. 36.46 grams of HCl on the bottom. And that's moles of HCl. And so now I've got moles of HCl on the top, so I need to put moles of HCl from the stoichiometric coefficients on the bottom. And then the 2 moles of water on top. And so when I do that conversion out, right, do 17.3 times 2, then divided by 36.46, then divided by 4, and I get 0.237 moles of H2O. So, same reaction, similar problem, only we're going to go, instead of stopping at the moles of water, they're asking us what mass of water forms, right? But it's the same idea. I'm going to start with grams of HCl. I want to know the grams of water. And so I need to go from grams of HCl to moles of HCl. So for that, I'm going to need the molar mass of HCl again. Let's rebalance this. To go from moles of HCl to moles of water, I'm going to use that 4 moles of HCl, 2 moles of water, and then to go from moles of water to mass of water, now I just need the molar mass of water. So my conversion factors right, we already found the molar mass of HCl in the last problem, so I'm not going to recalculate it. 1 mole and then I know 4 moles. 4 moles of HCl make 2 moles of water. And the last step, I need the molar mass of water. 16.00 plus 2 times 1.01. You may have the molar mass of water memorized at this point. 1 mole of H2O is 18.02 grams of H2O. So, give myself a little bit more room here. I'll start again with my 17.3 grams of HCl. The 36.46 grams of HCl needs to go on the bottom. So then the 1 mole of HCl on the top. And what I sometimes like to do is check them off as I use them. Right? So I don't have to look at that anymore. I've used that one. So now I need to get rid of moles of HCl. So I'll use the second one. I've used that one. And then 1 mole of water, 18.02 grams of water. And let's check and make sure everything canceled, right? So I have grams of HCl, canceled with grams of HCl, moles of HCl, moles of HCl, moles of water, moles of water. And so I'm left with grams of water as my final units. That's what I'm looking for, so that's good. So when I do out that math, 17.3 times 2 times 18.02 divided by 36.46 divided by 4, I get to 3 significant figures. 4.27 grams of water. So the key to stoichiometry is that we have to use moles. If I want to go from any one substance to any other substance, I'm always going to use the stoichiometric factors in the balanced chemical equation. And so to use those, I always have to go through moles. So what this chart kind of represents is everything on the left here is information I might know about the first compound they're asking about, and everything over here represents the second compound they might be asking about. And it doesn't have to be reactants and products. You could tell me how much product you have and ask me how much reactant we need to make that, and so it's essentially just going backwards from what we just did, but it looks exactly the same. Or you could give me how much of one reactant I'm starting with, and how much of the other reactant do I need to use that all up. And so I could go from reactant to reactant. But whatever they give us, the key is I need to get the moles of the first thing, then I can use the stoichiometric coefficients to get the moles of the second thing, and then we know lots of things that we can do with moles. Right? We can go from moles to number of particles. We can use molarity to go from volume to moles. In the examples we were doing, we were going from mass to moles, but if they gave us the volume of a pure substance as opposed to a mixture, we could use the density to get the mass and then the molar mass to get to the moles. So they could give us any of these different things: the number of particles, the volume of a solution, the mass, the volume of the pure substance. We've got to get that into the moles of the first thing, use the stoichiometric factors to get to the moles of the second thing, and then whatever they're asking for, that's how we'll decide what to do. If they want the mass, we'll just use the molar mass. If they're talking about solutions and molarity, then we'll use the molarity equation to get what they're looking for. If they want the volume of a pure substance, then we'll go from moles to mass, and then density can get us to the volume of the pure substance. So I think I probably have 2 final examples here, and then I have another video with even more examples, so you can see different ways that we might do this. So the reason I want to do this example is because in the previous couple, we were always going from a starting amount of reactants to the products, right? But we can go between any of the species in the chemical reaction. In this case, we're given the mass of chlorine, and we want to know how many grams of sodium are required to completely react with that. So here I'm going from one reactant to another reactant. and that's perfectly fine. It's going to work exactly the same way, and I need to go through moles. So they gave me 2.45 grams of Cl2, so I got to get to moles of Cl2, then I can get to moles of sodium, and then I can finally find the grams of sodium. To do this, I need to be sure my chemical equation is balanced. To do that, I think I need a 2 in front of the NaCl, and then a 2 in front of the Na. And so I need the molar mass of Cl2. I need the molar mass of sodium, and then I know that 2 moles of Na is equal to 1 mole of Cl2 from the equation. So molar mass of sodium, I just look at the periodic table, 22.99 grams per mole, or I like to write that as 1 mole of Na, 22.99 grams of Na. For Cl2, it's 2 times 35.45, so that's 70.90 grams per mole, or I like to write that as 1 mole of Cl2, 70.90 grams of Cl2, and then I have 2 moles of sodium, 1 mole of Cl2. So these are the conversion factors I'm using. And so I'll take my .45 grams of Cl2. I need the grams of Cl2 to go away, so I'm going to use the molar mass of Cl2 first. Then I'll use my stoichiometric coefficient, so 1 mole is 2 moles of sodium. Then the molar mass of sodium. Alright, so 2.45 times 2 times 22.99 divided by 70.90, and I get 1.59 grams of sodium. Alright, so one more example. I want to know how many grams of O2 must react to form 28 grams of carbon dioxide. In this case, they've already balanced my chemical equation, and I won't try to mess you up. I'm not going to put coefficients in the chemical equation and incorrectly balance it. So if you do see coefficients in the chemical equation, you can assume that I have balanced it correctly. So I'm going from grams of CO2 to grams of O2. So I need to go to moles of CO2. Then I can use the stoichiometric coefficients, where I know that 5 moles of O2 will react to give 3 moles of CO2. And then I can get what I'm looking for, the grams of O2. And so again, I'm dealing with masses, so I need the molar mass of CO2, and I need the molar mass of O2. So for CO2, (12.01 plus 2 times 16 is 44.01 grams per mole. So For oxygen, the molar mass, 2 times 16, so that's going to be 32 grams. And then my stoichiometric coefficients from the balanced equation, 5 moles of O2 is 3 moles of CO2. So let's see, I'm ready to do my problem now. I have the conversion factors I need. So I'm going to start with my 28 grams of CO2. It's going to be 3 steps, so I'll go ahead and put in the place for my conversion factors. I'm starting with grams of CO2. That needs to go away. So the only place I have grams of CO2 in my conversion factors is in the molar mass of CO2. So we'll use that one. Now, 3 moles of CO2, 5 moles of O2. I've used that one. The moles of CO2 cancel. And so finally, 1 mole of O2, 32 grams of O2. The moles cancel. And so now 28 times 5 times 32, divide that by 44.01, divide that by 3, and I get 33.9 grams of O2. Alright, so all of the examples here have involved masses. This video is getting kind of long, so I have a separate video where I do an example where we do stoichiometry with solutions and molarity.